Hello. In this lecture, we will see basic concepts behind probability theory. So I will start with the idea of joint probability. Joint probability. So joint probability gives the likelihood of two or more events occurring together at the same point in time. So let's say there are two random variables x and y. So they are occurring together. So the probability that the event x comma y, so they are occurring together. So this is basically P of x and y. So this is how we have to understand. Both are occurring together. Right? So let's consider an example, our classic example of tossing a coin two times. So what is the let's say the random variable associated with the first toss is x, and the random variable associated with the second toss is y, right? So what is the probability that x will be, let's say, head and y will be head, right? So as we know, probability of getting a heads is half, and probability of getting another head in another toss is half. So this is 1 by 4. So probability of x comma y is equal to probability of x multiplied by probability of y. So this is a formula for joint probability, given that the events associated with this random variables x and y are independent, right? So an event is independent, its outcome actually does not affect the outcome of the other event. So here I toss the coin first time and I get a head, right? And the next toss, so given that I got a head, should not influence the outcome of the next toss. So in that case we can say that they are independent, right? So we have to understand the concept of dependent events. So what is a dependent event? Let's see an example. Let's see an example of a horse race. So let's say there are 10 horses, and maybe there is a horse called Jack, and there is another horse called Jill. So they are going to have a race, and all the horses have equal chance to win, equal chances of winning, right? Now I say that uh, in that race, Jack won. Right? So what is the probability that the Jill has won the match? So what is this? Jill has won the match. So this is 0 because we stated that Jack has won the match, right? Now let's say Jack does not came first, right? Or does not won the match. So what you can say about probability of again Jill won the match? So what is this? So this is not 0 now, right? So because there is a dependency, right? There is a dependency of these two statements. There is a dependency. Then the probability is not 0. It has to change to. So Jack doesn't won the match. So remaining we have 9 horses. So there is a chance that 1/9 chance is that Jill will won the match, right? So the probabilities are different. So in this case, we cannot write probability, joint probability of x and y as probability of x multiplied by probability of y. So this statement doesn't hold. It doesn't hold, right? In the case of dependent events, right? So this statement doesn't hold for dependent events, right? So then we have to think how we can compute probability values in the case of dependent variables. So let's see this idea bit more in a clear manner using an example, right? So a fair coin, so this is an example. So a fair coin is tossed 3 times, right? And let x represents a random variable. Let x represents the random variable. The number of heads in the first 2 tosses, right? And let y represent the number of heads in the last 2 tosses, right? So x represents the number of heads in the first 2 tosses, and y represents number of heads in the last 2 tosses. So question is whether can you tell whether x and y are independent? or not, right? So let me read the question one more. A fair coin is tossed 3 times, and X represents number of heads in the first 2 tosses, and Y represents the number of heads in the last 2 tosses. So we have to find out whether X and Y are independent or not. So how can we go ahead with this? So let's try to enumerate the possibilities, right? So 3 tosses. So we have 8 possibilities. So head, 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 tail, head, tail, head, then head, tail, tail, and we have a tail, head, head, then we have tail, head, tail, then we have tail, tail, head, and finally we have tail, tail, tail. So we have 2 to the power of 3, 8 possibilities, right? 8 possibilities. Yeah. Now you find out probability of X. So what is probability of X? Probability of X is representing first 2 tosses. It represents heads, right? So you just try to identify. So this is one case, this is another case, 2 case, right? So you have 2 cases in which you will get and divide by 8. So this is 1/4, right? So what is P of Y? So this is also, there are 2 cases. So this case and this case, right? So this is 2 out of 8, 1/4, right? But what is P of X comma Y? So in the first toss 2 heads must come. In the second toss, right, 2 heads should come, right? In the X represents 2 heads occurring consecutively, and Y represents 2 heads appearing consecutively, right? So we can see that only this represents this case, right? So this is 1/8, right? So if the events are independent, so what is the criteria? We can write P of X comma Y is equal to P of X multiplied by P of Y. But in this case you can see that this is not the case. So 1/8 is not equal to 1/4 multiplied by 1/4. So the events are dependent, right? Yeah. So how will you handle the probability values when the events are dependent, right? So you can write the joint probability P X comma Y in the case of dependent events as P of Y given X multiplied by P of X. So this is a new term for us. So this is called a conditional probability. So given x, right, what is the probability that you will get maybe what is the probability of y given x? That means you know what is x, right, and what is the probability of y multiplied by the probability of x. So this is the formula that you have to use when you are dealing with dependent events, right? So let us see the terms. So this probability is called marginal probability. So we have this is joint probability. So let us try to understand the terms conditional probability and marginal probability with an example, right? So let us consider a case where we have a situation where we record the probabilities with, let's say, a disease. So I'm representing if there is disease, there is no disease, and one is representing there is a disease, and you have symptoms. You doesn't have a symptom, and one represents you have symptom, right? So let me plot it like this. So this is a distribution table representing the cases, right? And let me assign some probability values. Let's say you doesn't have symptom and you doesn't have a disease. So what is the probability? Let me this is 0.35, right? So you doesn't have any symptom, but you have the disease. So in the corona times, we have seen without symptoms a patient have disease, but maybe the cases are very less, so we assign a 0.1 probability for that, right? And you have a symptom, you doesn't have a disease. Let's say 0.05 is the probability associated with that, and so this should be 0.5. So you have symptom and you have a disease. This is, so the total should be 1, right? So 0.35, 0.4 and 0.6. So this is the total must be 1. Yeah. So this forms an example of a joint probability distribution of symptoms and disease. So disease, comma, symptom, right? So let me represent this is x and this is y, right? So p of x comma y, right? So let me take one example from this. So what is the probability that you have symptoms and you have disease, right? So this is by looking at this table, you know this is the case, right? So this is 0.5, right? So likewise you can write the other values as well, right? So but we are interested in looking at a different aspect of conditional probability. So probability of something occurring given the particular event occurred, right? Given that a particular event occurred. So let's say probability of x taking an value 1 given y is 1, right? So what is this value? Probability of x is 1, right? So this is our table. This represents x values and this represents y values, right? So x is 1, so this case, right? This case, and y is 1, right? So you will tempt that to write this is 0.5, but just let's see the other case as well. Probability that x is 0 and given that y is 1, right? So what is this? So this value, right? So x is 0 and y is 1, so this will be 0.05. but is this correct? So this should add to 1 because this thing should represent a valid probability distribution, right? So this together should be a valid distribution. So if you add this, it should be coming to 1, right? So sum of p of x is equal to 1 given y is equal to 1 plus p of x is equal to 0 given y is equal to 1 should add to 1. But unfortunately we cannot see that situation here. But you are actually concentrating here, right? So this part. So so how can we solve that? You can normalize the table. So we normalize this as divide by 0.05 plus 0.5. So this also we can normalize it as 0.05 plus 0.5. So this is the normalized value representing the conditional probability values, right? So let's see what is probability of y is true given x is equal to 1, right? So what is this value? So let's see here. So y is symptom is there, right? Given that x is 1. So how you are going to compute this? So y is 1 and x is equal to 1. So this is 0.5, but before computing that you have to see the other case also. So p of y is equal to 0 given x is equal to 1, and you have to add this to become a valid probability distribution, right? So what is this value? So where are you looking at this table, right? So we are looking at here, right? So this is y is equal to 1 given x is equal to 1. So this is 0.5 divided by, you have to normalize it, right? So this is 0.1 plus 0.5, and y is equal to 0 given x is equal to 1 is 0.1 divided by, so you have to normalize this. So this is 0.1 plus 0.5, right? So this gives the conditional probability values, right? So let's consider another thing. So looking at the same table, let's see, we are trying to let's say we are concentrating on this value, this table, right? So what is this basically? So probability of y, right? So you are considering probability of y equal to 1. So you can sum, right? So you can sum it as 0.05 plus 0.5, right? So 0.55. So this is the sum of probability values where y is equal to 1, right? So similarly, p of y is equal to 0 will be this is 0.45, right? 0.45. So what are they? So p of y is equal to 0 is equal to 0.45. So this represents the marginal probability, right? So you are only concentrating on while computing this, you are only considering without considering the x columns, you are concentrating on this and you are computing the value of probability of y is equal to 1 as well as probability of y is equal to 0. So these are called marginal, since they are coming on the margins. Historically it is called marginal probabilities. So similarly you can sum over the other way also. So you concentrate on these values. So what is this? Basically p of x equal to 0. So without considering anything else, you are going to add up this. So this is 0.35 plus 0.05. So this is 0.40, right? So similarly, p P of x is equal to 1 is what? So this part, right? So this is 0.12 plus 0.5. So what is this? 0.6. So let me write here. So this is 0.4 and this is 0.6, and you can see that here it should come as 1. So 0.4 plus 0.6 is 1. Similarly 0.45 plus 0.55 is 1, right? So the total probability should add to 1. So we satisfy that. So this is called marginal probabilities. So marginal probabilities, right? So this is a very important rule in probability. We have seen some important rules. So the marginal probability is stated as P of x is sum of your summing over the values of y, as we have seen in the example, the joined probability distribution. So this is a very famous rule which is called sum rule of probability. And we have seen another rule where we have stated that P of x comma y is equal to P of y given x multiplied by P of x, right? So this is called product rule. Probability, right? And we have to notice one more thing. So if you are considering joint distributions among between two variables, so the ordering doesn't matter. So this is equal to P y comma x, right? So you can write P y comma x as in the product rule. You can write it as x given y py. So these two rules are very important rules. So one is sum rule and another is product rule, and this is another way to write the product rule. So in this lecture we have seen a very fundamental rules of probability. So starting from joint probability, I have described joint probability with examples, and then we have seen what is the difference between independent events and dependent events, right? So in the case of independent events, probability of joined probability of two variables will be the product of independent probability values. But if the events are dependent, then you have to use the product rule to compute the joint probability distribution. Okay? And we have seen another important rule called sum rule, where you compute the marginal probabilities using the joint probability. Summing over the other variable, you take the joint probability and sum over the other variable, you will get the marginal probability of the variable, right? So other things will be discussed in the next lecture. Thank you.